In this video, we'll explore the idea of chain rule, or the rule for derivatives for composite functions. So far we've discussed simple functions. In this section, we're going to talk about the function within another function. Like, for example, f of g of x, where g of x is inside function and f of x is outside. Not to be confused with a notation. It doesn't matter what the actual function is called, but let's say we have f of x or y equals to 2x plus 5 squared. Well, it's fairly clear that 2x plus 5, for example, is inside of the function like x squared, which would be the outside function. Or, here's another example, square root of x plus 4. Here we have x plus 4 inside of the square root function. So how do we use chain rule? Let's jump straight to it. If we're trying to take the derivative of a composite function, then the way to do it is sort of like peeling an orange, essentially. We'll start with the outside, and then we're going to work our way to the inside. So we're going to start with f prime of g of x, where the derivative of the outside, leaving the inside intact, essentially, times the derivative of the inside function. Sort of like the chain reaction or chain rule, which is exactly what the name implies. Again, there is a way to derive chain rule, but we're just going to try it out and see if it works. So let's say if we have a function where 3x minus 1 squared, where the inside function is 3x minus 1. That's our g of x. So that's just handy to keep in mind. 3x minus 1 is the inside, and the square function, or x squared, is the outside. So how do we take the derivative? 2 comes down like it normally would, like if you take the derivative of f prime of x, that would give us 2x, right? Then we have same idea, 2 comes down, 3x minus 1 stays untouched, and the exponent becomes 1. We subtract 1 from the original exponent, times what is the derivative of 3x minus 1? Well, it's just 3. And usually we can combine something, like for example multiply 2 by the 3, and so we're going to get 6 times 3x minus 1. And again, yes, we can probably simplify it further, like distribute, but it's okay to leave it like that as well. It's not wrong either way. So let's take a look at another one. Here is an example with negative exponent. Let's say 2x minus 1 to the negative 2 power. Again, how do we take the derivative? We focus on negative 2 power, which comes down. Then we keep 2x minus 1 intact. And negative 2, now we subtract 1, it becomes negative 3. So that's the derivative of the outside. Times the derivative of 2x minus 1, the inside function, right, this one, which is just 2. And again, negative 2 times 2 becomes negative 4 times 2x minus 1 to the negative third power. Now hopefully it's clear to you why we didn't distribute in the previous example, while it was easy to do it. In this case, it's not that easy because it's negative third power, and we're not going to focus on expanding further. But that basically gets the job done. So let's take a look, and similar to the fraction examples in 4.1 in earlier sections, we can have, for example, f of x as a fraction, 1 over x plus 1 squared. And again, typically how we would deal with that is make it a negative exponent. We can bring it out of the denominator and make it x plus 1 to the negative 2 power. If this was not 1, then we would have a number in front of it, whatever it is. Now we can take the derivative similarly. Negative 2 comes down. Again, x plus 1 is intact, to the negative third power times derivative of x plus 1, which is just 1. And now we would put it back in denominator because the original function was in the fraction form with the denominator. So we can put a negative 2 stays on the top, and x plus 1 to the third power goes in denominator and becomes positive exponent. So that's how we do it. So normally chain rule is fairly straightforward once you get the idea of inside and the outside functions. Here's another quick example, 1 over x squared plus x plus 1 squared. Again, we can bring it out of denominator, make it the negative 2 power. And similarly, again, we can take a derivative. Here is the outside times derivative of x squared plus x plus 1, which is basically 2x plus 1. Then negative 2 and 2x plus 1, both of these, stay on the top because they don't have the negative exponent. And x squared plus x plus 1 goes to the bottom and it becomes a third power. And again, it's okay to leave it like that and not multiply out for this course. Here we have a radical example. Let's take a look real quick. If we have square root of x plus x squared, we can write it as a half power and proceed the same way. How would we do that? Again, it would be 1/2 comes on the front, x plus x squared to the negative half power times the derivative of x plus x squared, which gives us 1 plus 2x. Again, 1 plus 2x actually stays on the top because it's together with a 1. 1 times 1 plus 2x, that gets multiplied. And the 2 stays on the bottom, this 2, and it stays 2 times square root of x plus x squared. And that's how we can do it with radicals very similarly. Here is one where we have sort of a composite function, but it's also composed of 2 different parts. We have 3.1x minus 2 squared minus 1 over 3.1x minus 2 squared. And we can proceed similarly as previous examples. We can have 3.1x minus 2 squared. That's fine to leave it like that. But then a second piece, we'll bring it out of denominator and make it negative. Again, it's important sometimes to simplify the original function before jumping to the derivative. So we did that. And the derivative, and now we focus on one of them at a time. The first one is the square power, which comes down. The power becomes 1 times derivative of 3.1x minus 2 will give us 3.1 plus, now we focus on the negative power. So the negative 2, which is why it became plus, the negative times negative 2 becomes positive 2. And this becomes negative third power again times 3.1 is the derivative. So we can multiply 2 by the 3.1 in both cases. So we'll have 6.2 times 3.1x minus 2, which again, we don't have to distribute, plus 6.2 can stay in the numerator, and 3.1x minus 2 to the third power can go in denominator. Now let's take a look at the few applications, which of course is the focus of this class, or if you're taking business calculus or applications-based calculus. So here is an example where we must actually, before we get to applications, here is one that's a little bit more challenging, because notice now the inside function is a quotient. So if you recall quotient rule from before, previous section, or if you've studied it before, now we can use chain rule and quotient rule at the same time. It looks a little complicated at first, but try it a couple of times and you'll get a hang of it. So again, we focus on the outside function first, which is very simple. 3 comes down, function stays the same, and becomes squared power times, now we focus on the inside, which is the derivative. Again, the denominator becomes squared. And now, if you recall, we take derivative of the top, which is 3 times original bottom, minus derivative of the bottom, which is 2 times original top. And we simplified as before. I think we did this one in the previous section. We get 30 over 2x plus 4 squared, which actually it's okay not to simplify at this stage. I left it as is. Why? As we'll see. So if we separate the first two and make them both squared, notice how I rewrote this a little bit. 3 was on the front. It actually goes in the numerator because it's like 3 times a fraction goes in the numerator. Then we have 3x minus 9 squared, and we have 2x plus 4 squared times 30 over 2x plus 4 squared. Why did I separate them like that? Notice how the denominators can combine and make them a fourth power, 2x minus 4 to the fourth power, times 3 times 30 is 90 times 3x minus 9 squared. Probably would have been okay to leave it like that, but it's not a really simplified version, because if you notice, we can pull something out of both top and the bottom. So notice how 3 can come out, and remember we square it because 3x minus 9 shows up twice. We pull out 3 twice, actually becomes a 9. So we have 90 times 9 times x minus 3 squared, and on the bottom, actually, we could have done the same thing, but unless there's something to cancel, it's probably okay to leave it like that. So 90 times 9 equals to 810 times x minus 3 squared. Actually, it would have been more correct to go to the next step and simplify it further. X minus 3 squared, and then we can pull out the 4 on the bottom and probably cancel. Sorry, this actually becomes x plus 2 squared. Yeah, we could have canceled it more, but the focus is it's okay to sort of leave it in one way or another, but it's okay to also pull it out and combine it. Okay, so either one, whether you pull it out of the 4 out of the denominator and distribute and cancel, or you leave it like this, in either way would be fine. Probably would be more correct to simplify it further, but we'll leave it at that. Now let's talk about some application problems. Let me actually read the one that shows up on page 338, so for your reference. Okay, so I have it in front of me. So basically the problem is food versus education. If we have the percentage Y of total personal consumption an individual spends on food is approximately, and we have this function, if I can write it in a second. Is y equals to, if I can see it, 35x to the negative 0.25 power. Okay, and that's percentage points. It's a rather strange equation, but it's, again, in the context of business applications or different applications, it's probably not that strange, again, if we're talking about regression or getting equation. So we have, so again, y is the total personal consumption and x is percentage points, where x is percentage the individual spends on education. So x is not quite the food, but it's part of something else, which is education. And x is also depends on time, and it's 7 plus 0.2 t. And an individual finds that she's spending x equals 7 plus 0.2 t percent of her personal consumption on education, where t is the time and month since January 1st. So t is a number of months, this is equal, since January 1st. Okay, so use direct substitution to express the percentage y as a function of time t. Do not simplify the expression, which is helpful, and then use chain rule to estimate how fast the percentage she spends on food that is changing on November 1. Be sure to specify the units. So what do we have going on here? If we have direct substitution, notice how we can plug in this for the expression of x, so that's fairly simple. And then we can, we know that t equals 0 represents January 1. We have to be careful how we count. So that means t equals 2 is February 1, and so on and so forth. So November 1 is actually 11th month, but it's 10 months since January 1st. So you have to be careful how you count. So when we take the derivative, we can use chain rule, which is negative 0.25 times 35. That would give us negative 8.75 times 7 plus 0.2 t to the negative 1.25 power, again that's the outside, times the derivative of 7 plus 0.2 t, which is just 0.2. And again, 0.2 times negative 8.75 we can distribute, and that would give us negative 1.75 times 7 plus 0.2 t to the negative 1.25 power. If we plug in 10, use your calculators, I'm getting about negative 0.11 to the 2 decimal points, which is percentage points per month, because we're talking about rate of change, and it was percentage points, that was the y, and that's per unit of time, t, so that's per month. And that's basically the idea. This one was a sort of a strange example, but the idea is if you have one function that depends on another function. For example, your number of items can depend on time, how you produce them, and then when you sell them, let's say you can create revenue, can depend on X, which is a number of items, which is also a function of time. So your revenue can become a function of time. That's kind of the idea, how you can create function of a function. And here is another one that's, again, you have to think about very carefully. What if we cannot use chain rule explicitly? What if we do not have equations? That's basically what it means. But we can still use chain rule if we know both rates of change. So we'll take a look at that kind of example. Let's say we have this kind of idea, marginal revenue. The weekly revenue from the sale of rubies at RRR, I think it's something like Royal Ruby Retailers or something like that, is increasing at a rate of $40 per $1 increase in price. And the price is decreasing at a rate of $0.75, which is actually 75 cents, per additional ruby sold. What is the marginal revenue? Interpret the result. Basically what we're doing here is, if you're trying to take, if your revenue depends on, I believe, price, which depends on the number of items. So here we have a composite function. Revenue is composed of another equation, which is price, which is composed of X. How we take the derivative of it? Well, if we use the implicit way without the equations, here's how we can do it. We can take the derivative of revenue with respect to price first times, that's the outside, if you recall, we take the revenue times the derivative of the price, which depends on the number of items that you produced. Notice how dp cancels, and we can actually obtain derivative of the revenue with respect to just the items. So like the price is the intermediate variable that can get canceled. But how do we do this if we just know numbers? Well, we have derivative of revenue with respect to price. We know it's 40 because it's increasing. We have it positive. I didn't include the units, not to make it too confusing. dp over dx, that's decreasing, so it's negative 0.75. And now we can find the derivative, r prime, that's the derivative with respect to x, is dr over dx. And notice how I wrote it out right here. And so dr over dp, that's 40, times dp over dx is negative 0.75. We can multiply them so we get negative 30. And that's dollars per each additional ruby sold. So that's how we can equate without taking price into account. It's basically the revenue is decreasing for each additional ruby sold. So again, we can sell too many rubies in this case. And that's it for this section.